So the next kind of double displacement reaction of aqueous solutions would be an acid-base reaction. And so acid-base reactions are also called neutralization reactions. On your formula pages, remember all of your chapter 7 is formalized in this chart. So we've done our precipitation reactions where a solid formed is the driving force. Now we're moving on to acid-base reactions where the driving force is that water is formed. We're going to keep practicing that pattern of double displacement here as we take a look at these acid-base reactions. And so we know that an acid from our nomenclature has an hydrogen as the cation and then something else as the anion, either the non-oxy acids or the oxy acids when we named them. Bases, we didn't have a separate system of nomenclature to name them in that they're going to be a polyatomic, and so they have the hydroxide as the anion and something else as the cation, or so metal as the cation. So sodium hydroxide, potassium hydroxide, ammonium hydroxide. And so in these, we're going to stay true to that idea that these ionic compounds are going to dissociate when they're in water. And basically the acids release their hydrogen ion or their cation. When a base dissolves in water, they release their hydroxide ion. And so the the sodium would be in solution and the hydroxide would be in solution. This idea that these ionic compounds dissociate. So in all of these acid-base reactions, the hydrogen from the acid is going to practice this pattern of double displacement and combine with the hydroxide of the base, except for we're not going to write it as HOH. What we're going to write it as is a covalently bonded molecule of H2O. It's still roughly that double displacement reaction. The cation from the base is now going to combine or bond with the anion from the acid, and that makes an ionic compound, which we call a salt in chemistry as a very general term. You might be thinking of sodium chloride as table salt, but table salt is a salt, as is magnesium chloride or potassium chloride. They're all salts. So here we have our acid and our base. They're going to mix together. We're going to have this double displacement reaction. So we'll have sodium chloride in solution and the hydrogen and the hydroxide not forming HOH, but forming H2O. Now, H2O is a pure substance, and we put an L behind that pure substance. If we were to take a look at this and take a minute to write out the full ionic equation here, we'd have the hydrogen ion. I didn't start far enough over to the left. And the chloride ion, the sodium, the hydroxide, the sodium, the chloride ion, and thank goodness, so out of space, H2O. So that's the complete ionic equation. If I take a look at anything that is a spectator ion and remove that from my equation, I'm going to be left with the net ionic equation. And the net ionic equation for any acid-base reaction, again, shows that driving force of the chemical equation, or the chemical reaction, in that we have our hydrogen and our hydroxide forming water. And formation of water was that driving force of a chemical reaction. So here we have one for us to do on our own. We're going to go all the way with this. We're going to go through the molecular equation, the complete ionic equation, and the net ionic equation. And spoiler, that's going to be your net ionic equation. So we got nitric acid reacting with calcium hydroxide. Again, these are aqueous solutions. So HNO3 and calcium hydroxide be patient with your nomenclature if it takes you a little bit. There's definitely a huge process in understanding how you write these. Now I'm going to practice this double displacement pattern. So calcium nitrate and water. Not HOH, right? That would really illustrate that double displacement reaction or pattern, but that should work. So that is my molecular equation. The complete ionic equation would be all of these things that are aqueous shown. Oops, did I balance this? I did not balance it. I knew it. Goodness me. There we go. I see if I run out of room. They're definitely hand cramping exercises to do. And so that would be my complete ionic equation. So now I take a look at anything that's a spectator ion, I can sort of ignore, and I'm trying to form my ionic or my net ionic equation. So anything that's left behind would give me my net ionic equation. Oops, did I do something wrong? Oh, I did too. Shoot. Maybe you caught that already for me. See how I said if you mess up your balancing, you'll notice it at some point in the process? That's how I realized. So this one, you don't need the 2 out in front. Obviously the 2 came about because I had dutifully balanced this, but it's still that net ionic equation of our acid-base reaction or our neutralization reaction, really showing that driving force of formation of water of a chemical reaction.